How's it going, YouTube? It is the first episode of the Phase 4 study vlog, and I decided to do a little bit of a different format for Phase 4. So for this phase of Flatiron School, I'm going to be having my dad on these episodes with me, and I'm going to be explaining to him in the best way that I can the things that I'm learning in each module. He is a psychologist and not a computer person, so this will be fun to try to, a good challenge for me to try to explain these things in a way that makes sense to him, right? I feel like that's a good indication that I understand it pretty well if I'm able to explain it in a way that makes sense to somebody that's not in the know of like this sort of like machine learning and that sort of thing. So if you're new to the channel, if you're new to the series, what's basically going on is I'm a student currently at the coding boot camp called Flatiron School in their data science program. I'm in phase 4 of 5. We're getting into advanced machine learning concepts here. So if you're curious about Flatiron School or how to enroll in it, or what other opportunities it has and all that, that'll be linked in the description below, as well as the GitHub repository for all of the labs and things that I'll be using in this vlog series. Cool. So I don't know if you want to introduce yourself or your name or anything real quick.
I'm Robert.
Mm-hmm. You look at the camera, not the computer.
Okay.
Yeah, so they'll be able to see what's going on over here.
Oh, okay.
Yeah.
But I'm trained into this.
Right, that's what you want to pay attention to, the TV monitor over there. So normally I do I for phase 3 I was putting like a notebook together for these study vlog videos. That was a lot of work, and like the payoff for all the work wasn't really worth it for me. So I'm just going to be scrolling through some of the material provided by Flatiron School rather than through a Jupyter notebook like I've done in the past. So what this module was all about was something called principal component analysis, which is a type of unsupervised learning, as you see right there. So you remember when I was doing phase 3, I was telling you that I was learning all this supervised learning stuff, and that required like a label, right? So you would have like so many different columns, and that would be like what you were predicting with, and then one column would be like the label if it's 1 or 0, or you could have like 1, 2, 3, 4, or 5 or whatever kind of labels, but you needed like some feature that was like basically the answer sheet. Right, and then that's what you would test the model against, is how closely it got the answer sheet right. So this is unsupervised learning, and that's basically a way of unsupervised learning broadly is a mathematical approach to find kind of groups or patterns in the data without having a label. Right, so you're looking, it's kind of like how like one feature correlates with the other like mathematically. So don't worry about all like the text and everything. This visualization is what I wanted to show you. That's like after this whole module, this very first visualization that showed is the best thing to me that represents like what's really going on with principal component analysis, which is the type of unsupervised learning that I learned in this module. So you can see it's kind of going through iterations, and what's really going on is, like you've seen regression analyses before, where it has like the one regression line that goes diagonal. Basically, this is creating multiple regression. They're not really regression lines, but they're lines plotted nonetheless. And you can see that it kind of iterates through different ones until it finds the ones that separate these 4 different clusters the best. And the algorithm discovers like what the slope and intercepts of these lines are just through kind of like a mathematical algorithm. But so that's what's going on basically, is it's calculating what the slope and intercept of each of these lines is and how many different lines there should be based on the mathematical correlations between each one of these data points.
Okay, and that's what this is representing?
Right. Mm-hmm.
Okay.
Do you have any questions so far?
Well, my question would be is on some of your dots, like there's some of them are very concentrated, some of them are more scattered.
Right.
And how this line over here is representing which dots or which x's.
You're talking about this line on the right here?
Yeah.
So this is your sum of squares is what this is representing, and it's good when your sum of squares goes down, generally speaking.
Okay.
So what your sum of squares is like, so ignore like this for a second and imagine just like a regular scatter plot with like a diagonal line, right?
Okay.
So if I drew a line from each point to that regression line, and so I just had a bunch of lines like this, they'd be like on the bottom too. I would take the distance of all those lines, that's called your residuals, and I would square them and sum them all up. And that gives you a calculation of like what your overall...
That's what that graph is.
Right. It's showing, it's the square of the sum of residuals, the sum of squares. And the fact that that's reducing, that value, the sum of squares is going down, indicates that these lines are getting closer and closer to their best fit. Right, the further off the line is from the actual data points, because the line is a predicted data point. It's a vector that represents a set of predictions. So the further off that line is from its like respective data points, like the greater the residual is going to be, therefore the greater the sum of squares is going to be. So that's what that's showing is like, as like obviously that's not a really great like boundary line for like this cluster. So your sum of squares is pretty high. And as these boundary lines get closer and closer into these gaps here, meaning the sum of squares is less, like the that reduces. So that's just like a performance metric, basically.
Okay.
So a lot of times it's hard to like, it's difficult to really like efficiently visualize to this degree over iterations. So it's a lot easier just to pull like your sum of squares and look at that instead of having to. It takes a lot of computing power to make plots. So a lot of times when you like are just iterating through and you know it's not like the model yet, you know, you're just trying to like improve it. It's a lot easier to use just performance metrics like that than it is to actually like plot everything. So that gives you some idea of like mathematically what's going on with principal component analysis. What the whole goal of it is I don't want to go there yet. Is to reduce the dimensionality of a data set, right? So the same way it's like computationally expensive to produce graphs like that, it's also becomes exponentially more computationally expensive the more features you have in a data set. Right. And it's exponential, right? It's not linear.
Yeah.
So if you have like, you know, there's data sets out there that might have like 1,000 different columns or something, right? And it might not be efficient to train a model on so much data. So what PCA does is it reduces the number of features in a data set and by losing as little information as possible between all that data. So you could like randomly drop like different like features from the data set and be like, okay, but you're probably going to lose some like predictive power when you do that if you're just randomly dropping features. So what principal component analysis does is it's a way of compressing like 1,000 rows into like 100 rows or something. And it does that with some fancy math that kind of compresses all that information or as much of it as possible into those 100 rows instead of just, you know, randomly dropping like 900 of them or whatever. So that's what this notebook kind of illustrates. So this is like a data set of just like some faces. And you can imagine, like, for one, like, PCA could be used for, like, facial recognition if you're trying to, like, you know, cluster, like, the eyes and the mouth and, like, different stuff like that, you know? Like, it's pretty clear that there's, like, clusters of data, like, on a scatter plot here. It's a little less intuitive when you think about it. It, like, starts to make sense how that can be used to cluster different sections of an image, because that's ultimately just data to the computer, right? So PCA, there's kind of a workflow you go through. I'm not going to get into all the math and everything, but there's a checklist somewhere. It doesn't matter. So you can imagine there's a ton of data. These are pretty like high-res images, so there's a ton of data in here, and it would take a lot to label all the data and to do whatever you wanted to do like with that if you were doing kind of predictive modeling. So this is showing, like I said, it's also a question of like how many. Like this has 4 different principal components, and it's just trying to find like like the best fit lines. Maybe you want 5 principal components. Maybe you want 6 or 3. You don't really know, right? So this is showing you basically how much variance in the data is explained based on how many principal components you have. Which obviously you want to be able to explain more variance than not, right? So this tells you that you don't want 20 principal components, but if 100 is like taking a really long time to run, then like you probably get away with 90 or 95 and get just about 0.9. So that's what that's like showing. So there's different steps in doing PCA, and this is kind of showing like what one of these images looks like halfway through. So this is like if we took just the means of all the columns in the data set that represents this image, and you can see that's like pretty good. Like you can recognize that it at least that it is a face, right? So this is the compressed data set raw, if you will, before we like reproject it. So this is what happens to the original image when it's being compressed down with PCA. But using the right math, we can get, I think those are clearly different images, but you can imagine this being as fuzzy as that one was. And you can, from the compressed data, you can get back like pretty close to what the original image was. So like if you scroll up and look at, there's one of these guys. There's that image down there with the glasses. So that's the original image. I think it's that one right there. And then you look at that. He didn't have his lips open. That one maybe? One of them. Is that guy at least?
Yeah.
Right. So you can see like the resolution is, some of it's lost, but it's still clearly like that guy. Right. And so that gives you kind of an idea of what happens when you're losing some features. You're going to lose some information, but PCA is able to retain a lot more of the information than just like kind of vanilla compression would.
I see.
Yeah.
Okay.
So that is really useful for, there's probably better algorithms to use if you're trying to compress data for the sake of transferring data from one machine to the other. But for the sake of machine learning, if you're trying to evaluate a data set, this just kind of shows that PCA is pretty good at reducing your computational costs but also retaining a lot of the information, because we were able to reproject this image from the compressed data. So that's basically what's going on with PCA. And so, okay, so here's, you can see this is with 10 principal components or 20 principal components or 30 principal components. Now, principal components, we're saying features. So say if there was like originally 1,000 features, when we projected to 30 principal components, that's just saying we reduced it from 1,000 to 30 features, which is obviously going to be much easier to compute.
Which has to do with the line that went up like this and then over with a 30 was almost.
This is what that line represented, basically. Yeah. So that's basically PCA in a nutshell. What kind of questions do you have, or
when it comes to the principal components, basically the way I'm seeing it is the resolution just becomes more clear. And with one aspect, but the identifying capability at 30 principal components is as good as 110.
Right.
Yeah.
So 110 would be kind of like overkill.
Right.
Yeah. I'll wait. All right, and we are back. Let me get you in frame. There we go. Okay, so yeah, you picked up on intuitively that this is kind of showing that beyond like maybe 70, 80 principal components, you're really not gaining much in performance.
Right.
At that
point.
Yeah. Which is part of like my job as a data scientist is to figure out what that number is, how many principal components.
Yeah.
You need. So you prototype, you'll build, like a dozen different models with, varying amounts of principal components, and then you'll evaluate the performance metrics of each one and pick the one that is the best. And, like depending on like the purpose, this might be good enough. And that's kind of where your domain knowledge comes into play. Like for just purely for aesthetic reasons, like this is the easiest one to look at for me.
Right.
I guess this one, like technically, but it
once
doesn't
you
get much better
once
after
you get
that.
to there, yeah.
Right.
Yeah.
But for your specific purposes, like 40 or 50, that might be enough for what you're doing. And that gets into like your specific problem that you're solving.
Would that be similar to like your facial recognition on your computer to open it up?
Mm-hmm.
And so you could probably get by with a much lesser number of components or something.
I don't specifically know like what software they're running for those things. I imagine you want it to be pretty good, but it doesn't need to be like it needs to be pretty good to the computer, not necessarily pretty good to the human eye.
Right.
Yeah.
Yeah. Well, I was just thinking the difference in your personal phone deal or some secure facility at the CIA or somewhere where it would need that you would definitely.
Well, so what they do is there'll be some research team with some data scientists and some data engineers and like different people like that, and they will build a model, which I can actually show you in this notebook, I'm pretty sure. This variable right here, like that contains the model, right? So this is a model being built right here. It's a support vector machine, which there's a ton of different types of models. There's decision trees and linear regression, blah blah blah. So support vector machine is just one type of model. What is going on here is, remember I was saying you have to kind of prototype different models. This is what this code represents is basically like, can I start myself, please? I guess not. So imagine like a list of numbers, like 1, 2, 3, 4, 5, all separated by a comma. What this is saying is it's saying give me 11 different values evenly spaced between 0.1 and 10. You create a list of that. So that's what's going on there, right? And so you can imagine like this all together makes a grid of 11 different values for C, which I don't even fully understand what C is, but it's something that you're supposed to like experiment with different values. Gamma, the same thing. And so what's going on here is it's looking at all the different possible, it's building a model for each different possible combination of these two things, of each value in this list. And then it's returning to you the combination that gives the best performance on whatever your performance metric is that you chose. There's different metrics that you use for different things. And so that's what it's telling me here. Is that these were, of all the different combinations, these are the ones that produce the best performing model. I kind of lost my train of thought, but so that's like what you're talking about, facial recognition. So what they'll do is they'll do this kind of workflow, much more in depth, right? Because these large companies, they have like months and months to develop this stuff. But they'll eventually arrive at a model that is, achieves their goals, whatever their needs are. And then they'll do what's called pickling that model, which is basically compressing the model itself so that it can be exported and sent to other machines. It takes, so right now, like on a computer, you have memory and you have storage, right? Storage is like the stuff like in your files and folders and like things that like anything in storage is something that when you turn the computer off, like completely shut it down and boot it back up again, it's still there. That's what's in storage. Okay. Memory is anything that when you shut the computer down and boot it back up, it's not there anymore. Oh. Right. So like these notebooks that you see me running, when I close the notebook, even not even shut down the computer, and I reopen it, I have to rerun each one of these cells. All this information, all this stuff that's been built, like when I run the cell, it just disappears. Okay. So because it's just kind of being like held in the ether until I shut down the notebook and then it disappears. Which is why I end up staying up pretty late sometimes working on this stuff because I don't want to shut the notebook down and wake up in the morning and have to rerun it for like 30 minutes, like just to get back to where I started. Right. So, what they'll do once they get a model that's like, that they're happy with, then they'll pickle it, which is just a way of saying like they export it into they'll package it into like a file, the same way you can download a CSV file, or like an Excel sheet or whatever, and package it in a way that it can be downloaded. And then that actual code that is like that model will be installed into like the devices that they're using the facial recognition on. Okay. So that's what they'll do is they'll build a machine learning model, and then once they have like they finally get the model that's like like succeeds at their goals, then they'll export that into like an actual file and install it into the hardware in like whatever devices. Yeah. So it's not like getting like trained necessarily. It's not retraining a model every time it reads your face or whatever. It's like the same model running every time. Yeah. But it's that's where it all starts, is like something like this. Yeah, and then for computers purposes, especially if it's like dealing with like UV or infrared or something, then you can maybe get away with even less resolution for your photos. Yeah. Which is another way of like kind of reducing your computational complexities, capturing the photo in a different format. That where it might be nonsense to a human, but it will be even more information to a computer, but with less features. So, and I'm sure that's another thing that they experiment with. They probably will have like photos taken with different types of like lighting or like UV or infrared or whatever, and they'll test like all these models with all these different types of like photos and all that. Like I said, these big tech companies, they have the time and the money to
Can I ask just a crazy question? Okay, let's say at the
I'm not sharing the screen. It's okay, we're good. Okay.
Let's say at the 40 principal components I'm imagining a facial recognition thing. Okay, the glasses this guy has on, so everything's good. If he changes glasses, then theoretically, I'm just hypothetically, it may be at one of those components it wouldn't recognize him, whereas this one down here that's got so many comparisons that it would still recognize that face even with different glasses.
Right, yeah. There's some amount of information that it needs to... A good enough model would recognize the frames as noise. And there's noise and data.
But that's why
a good enough model would recognize that. But for that model to be so good, it needs enough data to be trained on to be that good.
In terms of those principal components.
Right. Yeah. The facial recognition specifically, I don't know that they definitely don't strictly use PCA. I mean, there's other algorithms that will like classify like landmarks on the face and measure like the distance from like the eyebrow to the cheekbone or like something like that. Okay. And like that obviously would like get around the issue of like the glasses like being
Right.
there. If you were doing strictly PCA, you would need so many principal components to get around this whole glasses thing that it would almost not be worth it to do PCA.
Okay.
So PCA is usually, it's more often used for pre-processing. Like you can build a model with PCA alone, but it's mostly used for pre-processing the data. Meaning, so when I say pre-processing, it's all the stuff you do to the data before you start building the model.
I got you.
That you have to build some models to evaluate
Right.
how the PCA is performing. So the next thing I want to show you is what you've seen, like kind of visually what's going on with PCA. Now I want to show you like more or less mathematically what's going on with it. I'm going to try to keep this as like low level good as possible. Okay, so this is our data set, and this is just the first 5 rows. There's hundreds of rows here, but this is all you really need to know, right? Is what your columns are and like what types of values are in each column, right? Fortunately, this is all in computer science we call floating points, which is a computer science word for decimals. You have floating points. This is actually integers because this whole column is 1, 2, or 3, or 0 or 1 or 2. Sorry, three different possible values. Okay. But sometimes like the target, a lot of times from like my last project, the target was binary. It's either 0 or 1, and that's called Boolean value. So anyway, we have this data set. What this is, it's different flowers, different types of flowers. And this, the 0, the 1, or the 2 corresponds to a type of flower, right? And this is the information about the petal length, petal width, blah, blah, blah. You can conceive how you could, with enough data to train a model, you could train it to identify the species of the flower just based on the morphology of like the leaves and whatnot, right? So that's kind of like broad strokes what's going on here. This is called a scatter matrix. I wonder if I can zoom out so I can fit this whole thing. Yeah. So the diagonal you see here is the feature corresponding with itself. So you see sepal length here and sepal length here. So this is just the diagonal. All of these are just like the distribution of like the respective feature, right? So this is like the distribution of different sepal lengths, right? The scatter plots you see here are the scatter plot of a given feature against some other feature. So this scatter plot represents sepal length on the x-axis and sepal width on the y-axis, and it shows how those two features like distribute with each other, right? So this is like, this data point is like the only one that happens to have that exact sepal length with that exact sepal width, right? And so this is usually look at this sort of plot at some point or another just to see, like you can already see like some of these are showing us some clusters. Like this cluster is probably also this cluster, I'm guessing. Yeah, and like this plot I think is petal length, sepal length, sepal width. Okay, or yeah, petal length, sepal length. Yeah, so this is the exact same. Basically everything on this side of the diagonal is a reflection of everything on this side. You can kind of choose which one you want to look at. But you can see here like we have pretty similar clusters. So you can imagine like you could have a scatter plot, you could have a 3-dimensional scatter plot where the clusters would be like at varying depths of on the z-axis, right? So like imagine I've got a scatter plot down here. Good. What was I saying about the scatter plot? Yeah, so imagine like right now it's like has colors to represent like the different clusters. But you can imagine if they were all the same cluster but it was a 3-dimensional plot, those clusters would be like at different depths.
Oh, yeah.
Right.
Okay. Right.
And so PCA is a way of taking like those 3-dimensional clusters and compressing them into a 2-dimensional plot like this, which this doesn't represent that because we have the colors to distinguish them. And that doesn't mean anything to the computer, but you can imagine like with some fancy math you can adjust these points to different positions where they're kind of like averages, if you will, of like the point versus the other two like clusters. And again, like we can't really get super in depth in the math there because it gets like pretty heady pretty quick.
Yeah.
But if you took this data set and compressed it into PCA, you could represent this same information represented by this scatter plot without the colors. The dots would be in different positions, but you could reconstruct this from that, right?
And instead of it, I mean, that's supposed to be 3-dimensional, right?
Right.
And so if you compress it, then what do you got? 2-dimensional?
Yeah, it would look different, but the same information could be gleaned from it.
Okay.
So remember, this is like our original data. So when you're doing PCA, the first thing you're gonna do is this is scaling the data. So imagine like different features might be on different scales. So when I did like the real estate pricing project, like the square footage of a house and let me think. I'm thinking back to like 3 projects ago. The square footage of a house and like its zip code or like its coordinates or something are like obviously not on the same scale, right? So you use scalars to kind of force everything to the same scale, so it's like comparable. So these 2 columns represent what is represented by these 4 columns.
Okay.
So this data frame right here, which is a spreadsheet in essence, is basically the same, or it represents the same information that original data frame does, right? So these numbers are completely different, and obviously to like a human or like even to a computer, any one of these numbers is pretty meaningless.
Yeah.
But this data frame right here could be reprojected back to the original data frame. And so that's kind of like your proof that it represents the same information. It's because you can reverse engineer it.
Yeah.
Mm-hmm.
Okay.
I thought there was one more visualization here that I'm going to show. Yeah, and that's just a different way of showing how it like draws the decision boundary. If I was doing this like for work, I would probably keep working on this a little bit because you see these burrs here that stick out, and it's trying to capture these data points with this group. See all these blue here belong in like the tan. That's probably overfitting. That's a great example of what I mean by overfitting. Is that you can imagine if it just like zigzagged or like this. If we had like just something like straight out here and just captured that, that's probably an anomaly because of how close it is to all these other data points that are from the other group. Right. So if you just like over-tuned the model to capture that specific data point, you're probably fitting it to the specific data set and not the population of all of the iris fibers in the world. Yeah. So that's what I mean by anytime you hear me say overfitting, that's what I'm like kind of referring to. Yeah. So, in summary, principal component analysis is a way to identify clusters of data, or in other words, labels, without having those labels in the first place. And you can create a pretty good model with it on its own, but more often than not, it's used to pre-process the data. So what I mean by that is instead of feeding the model this data, we can feed it only this and exponentially reduce the computational complexity required. And if you're dealing with something that has, like 100 columns and like 1,000,000 rows or whatever, that really matters. With this particular data set, small enough anyway, it wouldn't really be a necessity in like a professional setting. But you can see like,
understand what it's doing.
Mm-hmm. Yeah, and there's a kind of like a checklist you go down to get to this point. You like calculate the mean of each feature, and you subtract the mean from each value in that feature, and then where it really gets really mathy is you calculate what's called an eigenvector and an eigenvalue. And a vector is basically just like a list of numbers. And so that eigenvector is what becomes like your new feature, basically.
Okay.
And they didn't even begin to go into like the actual math behind calculating an eigenvector. They were just like, here's the code library that you use which is probably for the best.
Yeah.
As long as you understand what it's doing, you don't necessarily need to be able to write the proof by hand, Yeah. So that is principal component analysis, and that's what I learned in the first module of Phase 4.
And let me see if I can summarize that. What you were doing, you were taking data, and it was doing this analysis where it presented labels for what it was determining, or it determined things that you could label because you started without labels in order to identify certain things.
Sort of. So with the grid search thing that I was showing you, basically what that's doing is it's trying like 6 different regions and 5 different regions and 4 different regions until it's finding the one where the sum of squares is the least. So you can imagine these ones where, if you let it restart in a second, where they're like basically slicing through these clusters, your sum of squares is going to be like way high. Right, so what the analysis part of principal component analysis is doing is you're trying to find what the like ideal number of principal components to use is. And then once you know what that number is, then you build a model with that specific number of principal. You basically you tell it when you're building the model, give me 5 principal components or 6 principal components or 7 or 100 or whatever, right? So the analysis part is analyzing like their sum of squares or whatever other performance metric to figure out what number of principal components performs the best. And then once you know that number, then that's the data that you use, compressed to that specific amount of principal components.
Okay. All right.
So you'll try it with so many different ones, and you'll find the one that performs the best.
Right.
And you usually do that by, this is showing with your sum of squares, but you also use it with your explained variance, which was that other curve that you saw. Yeah.
Okay, you get all that, Zeus?
So, any more questions?
No.
So do you feel like if you heard about principal component analysis like on the news or read it in like
I would
morning or something,
kind of have a grasp of what they were talking about.
Yeah. That was kind of my goal, is that you have like a bird's eye view of like you're at least aware of what they're talking about and like what it relates to.
Right. Yeah. Which I never really remember paying attention to hearing that terminology.
Yeah, this is pretty obscure unless you're like specifically working with like heavy statistics or machine learning or something. I don't think you would come across this by chance. If you kept up with like the news around technology, then you might hear about it. But even then, that's still getting kind of domain specific.
Yeah, if I saw PCA, it's something I'd have no idea, but now I would maybe go, oh, I bet that's the
right. Yeah.
Could be something else, I guess, in some other field.
Probably,
maybe,
yeah.
Different,
But I'm sure PCA is used in any field that uses statistics. So, like, if you're a researcher, like in academia, like, depending on
you would, statistics, you would recognize.
Right. Yeah. Cool.
All right.
Well, that is it for this study vlog. This has been module 33 of phase 4. I hope you learned something. I hope you enjoyed it. Like I said earlier, if you want to explore the GitHub repository, connect with me on LinkedIn, or check out Flatiron School, all those links will be down below. And with that, we'll see you in the next study vlog.